what are the properties that enable these spherical mirrors to be so special? In today's lecture, we're going to find this answer. Here I welcome all my dear students of class 10 physics, topic light, subtopic spherical mirror, lecture number 2. Here are the books which I have referred. Learning objectives for today's lecture. Student will be able to understand what are spherical mirrors and type of spherical mirrors, basic term related to spherical mirrors, relationship between the focal length and the radius of curvature. In general, a spherical mirror is a circular piece of glass cut from a hollow sphere. Now, depending upon which side of the glass piece is silvered, the spherical mirror may be classified as concave mirror and convex mirror. Imagine this to be a spherical glass. Now, I will cut a piece of this glass from either end. I can cut from this end, or else I can cut from this end. It doesn't matter because it is still the remaining part of that is still a glass. Now, what important is, after cutting piece of that glass, which side is silver coated? Now, this side is inward and this is the outer side of the surface. So, after cutting the glass, what important here is which side is silver coated. So, if this side is silver coated, which will represent by drawing an oblique line, that means the outer end or the outer surface is made opaque by silver coating. So the inward part or the inner side becomes a reflecting surface. So this is a concave mirror. Now similarly, for convex mirror, the inner surface is made opaque. The inner surface is made opaque by silver coating, which is represented by the oblique lines. So in case of convex mirror, the outer end becomes the reflecting surface. In case of concave mirror, side E indicates the reflecting side while the other side is opaque, while in case of convex mirror, side F indicates the reflecting surface while other side is opaque. Some of the students get confused between concave mirror and convex mirror while drawing a ray diagram, that which side is reflecting or which side is opaque. To avoid such confusion, we'll create a simple analogy. So this is a concave mirror. As the name suggests, concave, cave, and you all are aware what cave is. So if we observe this cave, we'll find out that there is a space for any human to enter, or any kind of animal to enter, or a ray of light to enter. Similarly, concave mirror, concave, this part is a cave part. So when a ray of light enter, this part will act as a reflecting surface while other part will act as an opaque part. Here now we can define what concave mirror and convex mirror is. A concave mirror is that spherical mirror in which the reflection of light take place at the concave surface or bent-in surface. So this surface is the inward surface, which is represented by ERS as the reflecting surface, and the outward surface is painted by and shown by an oblique lens or bulging out surface. So this is a keyword for convex mirror. So here outward surface is represented by FRS. So this surface here, FRS, is the reflecting part, and the inward part is silver coated and is represented by the oblique lens. Now, in this activities section, we will only require a medium size shiny steel spoon. So what I want from all of you is to participate in this activity. So here, the surface of the spoon curved inwards can be approximated to be a concave mirror, while the surface that is bulged outwards can be approximated to be a convex mirror. While doing this activity, I want all of you to answer these three questions. The first two questions is for the concave surface and the last question is for convex surface. Now, if we hold a steel spoon close to our face, what do we observe in this concave side? If we move the spoon slowly away from our face, does the characteristics of the image changes in the concave side? Now, if we reverse the spoon, that means we are observing in the convex side, how does the image look now? You can list down the answers of all these questions and you can write down in the comment section. We will now introduce a few terms which are needed to study for the image formation by a spherical mirror. The terms are center of curvature, pole, radius of curvature, aperture, principal axis, principal focus, focal length. Now, similar to center of curvature, you have come across a similar term in your lower grade, maybe grade 6 or grade 7. Let me help you to recall this memory. Suppose we are constructing a circle of radius 6 cm. For that, we will require a ruler, a compass, we will first place the pointer of the compass at the initial point of the ruler and extend the other end of the pencil measuring 6 cm from the initial point. Now we'll mark a point C on this paper, and this point is supposed to be the center of the circle. Yes, exactly. Very much related to the center of curvature. In the next step, we'll place the pointer of the compass at point C. We'll make sure that the distance between the pencil and the pointer should be 6 cm, as we need a circle of radius 6 cm. Now we'll turn the compass slowly in order to get our circle. Since I just need the curved part of the circle, instead of drawing the whole circle, I will draw only the curved part. So here is the curved part with a radius 6 centimeter. Let me draw an oblique line first, which will indicate that the mirror is a concave mirror. So the first term is center of curvature. Let me draw a radius. So center of curvature can be defined as the center of the sphere of which the spherical mirror is a part is called the center of curvature of the spherical mirror. Let me define a new term. This term is P. So P here stands for pole. The center of the reflecting surface of a spherical mirror is called pole. The distance between the pole and the center of curvature of the spherical mirror is called as radius of curvature. So you can see in the diagram here that center of curvature for concave mirror is in front of the mirror, while in case of convex mirror, C, center of curvature is behind the mirror. Here's the definition for center of curvature and pole. Radius of curvature. Now aperture. Now aperture is the surface of mirror that is exposed to the incident of light. In case of concave mirror, it is MN. Here, the reflecting surface MN is the aperture. Similarly, for convex mirror, the reflecting side, the MN, is the aperture. The straight line passing through the center of curvature and the pole of a spherical mirror is called its principal axis. Principal focus for concave mirror and convex mirror will define separately. Once we understood the concept of principal focus, we will also understand the concept of focal length. So here we will discuss about principal focus of a concave mirror. Let me first increase the length of principal axis so that we can identify it properly. So this is my principal axis. It now shows center of curvature. So this is my center of curvature. Now if we observe this ray diagram, you'll find that the beam of light is parallel to the principal axis, fall on a concave mirror, and all the rays after reflection meet at a point on the principal axis. Now this point is called the focus point or focal point of the concave mirror. Since all the reflected rays actually pass to the focus of a concave mirror, therefore concave mirror has a real focus. The principal focus of a concave mirror is a point on its principal axis at which all the light rays which are parallel converges after reflection from the concave mirror. So concave mirror is also called converging mirror. Similarly, we can define principal focus of a convex mirror. Let me again increase here the length of the principal axis. So here somewhere center of curvature be there. Now this is a convex mirror. The outward is the reflecting surface while the inward has been silver coated. So if a beam of light parallel to the principal axis, if a beam of light parallel to the principal axis on a convex mirror, all the rays diverge after reflection. Now if the reflected rays are extended backward, if the reflected rays, all the reflected rays are extended backward, they appear to come from a point on the principal axis. Now this point is called the focus of the convex mirror. The principal focus of a convex mirror is a point on its principal axis from which a beam of light rays initially parallel to the principal axis appears to diverge after being reflected. So a convex mirror is also called as a diverging mirror. Difference between concave and convex mirror. Concave mirror, reflection takes place at the concave surface or bent-in surface, while for convex mirror, reflection takes place at the convex surface or bulging out surface. This is the definition for concave mirror and convex mirror. A parallel beam of light falling on this mirror converges at a point in front of the mirror after reflection. We have just discussed this topic in principal focus. Similarly, a parallel beam of light falling on this mirror appears to diverge from a point behind the mirror after reflection. Concave mirror is also known as converging mirror, while convex mirror is also known as diverging mirror. Concave mirror has a real focus. That means the focus point for a concave mirror is in front of the mirror, while in case of convex mirror it has a virtual focus because the focus point of a convex mirror lies behind the mirror. Since concave mirror has a real focus, concave mirror can form real image. Real image, while convex mirror will form only virtual image. Now let us see the difference between the real image and virtual image. A real image is formed when two or more reflected rays intersect at a point in front of the mirror. Now since concave mirror, focus point lies in front of the mirror, hence concave mirror can form real image. While in case of virtual image, a virtual image is formed when two or more reflected rays appears to intersect at a point behind the mirror. Now similar case also happens in plane mirror. Hence, plane mirror and convex mirror will always form virtual image. They will never ever able to form the real image. So the real image can be obtained on screen. Virtual image cannot be obtained on screen. It is inverted upside down with respect to the object. It is erect with respect to the object. Now the third point will understood once we are able to construct a ray diagram for different cases of concave mirror. It has been found that for spherical mirrors of small apertures is and dash, the radius of curvature is equal to twice the focal length. Now remember here, the keyword I am using here is small apertures. This relationship is true for both concave and convex mirror. This implies that the principal focus of a spherical mirror lies between the pole P and the center of curvature C. Here we will try to derive this relation that radius of curvature is equal to twice the focal length. As there is no such derivation in your textbook, but I am pretty sure that you will understand this as it is related to grade 8 and grade 9 geometry. With the help of lines and angle chapter, we will try to derive the relation. Now here if you observe line AB, that is ray AB is parallel to the principal axis CP. So let me draw ray AB is parallel to principal axis CP. The dotted line shown here, ray BC, we consider this to be a transversal line. This transversal line acts as a normal, therefore angle ABC is equal to angle CBF. Reason will be law of reflection. As ray AB is parallel to principal axis CP, therefore angle ABC is equal to angle CBF, as CB acts as a transversal and the reason being alternate angles are equal. As angle ABC is equal to angle CBF, reason law of reflection, and angle ABC is equal to angle BCF, therefore in triangle BCF, angle BCF is equal to angle CBF. As two angles of these triangles are equal, we can now consider triangle BCF to be an isosceles triangle, and hence side CF is equal to BF. Since we have considered aperture to be small, point B is very close to point P, and hence BF is equal to FP. As CP is radius of curvature and point F lies on CP, therefore we can write CP equals CF plus FP. As CF is equal to BF and BF is equal to FP, therefore we can say that CF is equal to FP. As we know that the distance between the pole of the mirror and the focus point is known as focal length, so we will write FP is equal to F, which indicates focal length, and instead of CP we will write R as it's the radius of curvature. Hence here we derive the relation that radius of curvature is twice the focal length. Check your progress by solving some questions. Name the mirror whose focus is from A, in front of the mirror, B, behind the mirror. Name the mirror which converges light, B, diverges light. Question number 3. The radius of curvature of a spherical mirror is 90 centimeter. What is its focal length? Question number 4. If the focal length of a concave mirror is 20 centimeter, what is the radius of curvature? Question number 5. If the sum of focal length and radius of curvature is 30 centimeter, what is the focal length of that spherical mirror? That's it for today. If you have any doubt regarding the topic, you can post it in the comment section. Until next time, stay indoors, stay safe. Thank you.